All right. So we're going to be working and doing simplifying with our trig identities. These are all our trig identities over here. And if it also helps, you can also put like the sign. We have a baby here that when we are simplifying, I'm going to keep trying to say simplifying, the easiest way to simplify with our trig identities is to put everything in terms of sine and cosine. Put everything in terms of sine and cosine so that we can then simplify like things. So what we mean by that is when we're looking at cosine of x and tangent of x, I'm going to rewrite this as cosine of x times, and the way we write tangent, so sine over cosine. So this is sine of x over cosine of x. And what can we see that's going to happen here? The cosines cancel out. So cosine x tangent x is the same thing as sine of x. So this is our answer. Good. So we're going to put everything in terms of sine and cosine so that we can simplify. So then we have cotangent and cosecant as our next one. So our cotangent, when we write that as a fraction, cotangent, that's our cosine over sine. So cosine of theta over sine of theta. And our cosecant, that's our inverse of sine. That's 1 over sine of theta. Right? See that? When we got these big old monster fractions by reciprocal. So this becomes cosine theta over sine theta times the reciprocal, which is sine of theta over 1. What happens? My signs cancel out this time. So we're left with the answer cosine theta. So write everything in terms of sine and cosine and then simplify. Questions on these two? Because you know they're going to get more. As soon as my computer decides not to be a grumpy ass. But I forgot my iPad at home, which is why I'm working with all kinds of fun new things. All right. So now I've got secant x, cotangent x, minus sine x. So first thing I'm going to do is write the secant x, cotangent x in terms of sine and cosine. So secant x, how do we write secant? 1 over cosine. And cotangent is cosine over sine. minus sine of x. What happens up here that we can simplify? My cosines are canceling out. So it's 1 over cosine times cosine over sine. So we have 1 over sine x minus sine of x. And I'd really like to combine those together. When we have fractions, and I want to combine them together, what do they need to have? Common denominator. Exactly right. So if I want this to have another denominator, what can I do? If I would like it to have a different denominator. What if I wanted it to have a denominator of 3? What would we do? Yeah, if I wanted it to have a denominator of 3, we'd multiply by 3 over 3. Or 4 over 4. Or I want it to have sine x as a denominator. So we're going to do sine x over sine x. So that we have that common denominator. So we're going to have 1 over sine of x minus sine squared x over sine of x. That way I can combine them together. I have 1 minus sine squared x over sine of x. And that helps. Oh wait, I see a 1 and a sine squared. I see a 1 and a sine squared. I wonder if I can solve and get something like this. So what we're going to do, it's going to take that Pythagorean identity. The sine squared plus cosine squared equals 1. And if I get cosine squared by itself here, we take our sine squared plus cosine squared equals 1 and subtract sine squared from both sides. Cosine squared equals 1 minus sine squared. 1 minus sine squared. This becomes cosine squared of x over sine squared of x. Our goal when we're simplifying is to get rid of as much stuff as we can. Not sine squared, sine x. Sorry, doing this for that denominator. Our last piece in here should go, wait, I wonder if I can rewrite that so I don't have any denominators. I'd like to get that sign out of the denominator again. So I can rewrite this. Cosine squared becomes cosine of x times cosine of x over sine of x. Cosine over sine? Cotangent. So this becomes cosine x cotangent x. And I don't have any adding or subtracting anymore. I don't have anything in the denominator anymore. And I don't have any like superfluous exponents or double things. So I know it's kind of weird and super awkward to get used to. Like that's totally normal for these to be awkward and weird. I think they're actually going to get my recycling this. Okay, so cosine x, cotangent x, that's our answer. questions on this, because I know it's weird. Yeah, they're just they're multiplied together. It's cosine of x times cotangent of x. Okay. Yes, dear. The sign on the bottom became part of the cotangent. Because cosine squared is cosine times cosine. That's what it means to be squared. And I can, like, chunk this out. Since they're being multiplied, this is just cotangent. Since they're being multiplied, we can do that. And I know, these are weird and super awkward to get used to. And these are weird and super awkward to get used to. And we're going to use them a bunch. You'll need to know these. Like, you need to know these. Okay, we're going to keep working with them. Questions on the first one? Okay. Oh my god, there's a button. I love it so much. I forgot my iPad at home, so we're just like, it's all good. All right. Boop. We're not gonna do that one. I don't like that one at all. Sorry. That's the thing in there that I'm like, I genuinely don't know where that came from. Sorry. Genuinely, I have no idea where the thing in the notes came from, and I don't want to try to explain it to you if I have no idea what I'm writing. So we're gonna do this one. This one makes sense. Okay. So our first step here is we are going to write as many things in terms of sine and cosine as we can. So this numerator, I want us to think of this whenever we see a 1 and a sine squared, or a 1 and a cosine squared. I want you to think about this top identity here. Because if I see sine squared and a 1, that means I can work cosine in somewhere. So let's see what we can do to make this guy match that. So our sine squared theta plus cosine squared theta equals 1. But I want it to be sine squared minus 1. So what do we need to do? Say it louder.
Subtract sine squared theta from each side.
You could subtract sine squared from both sides. Definitely an option. Another option, since I know I want my sine squared to be positive, how about we move that cosine? Totally fine, you'll still get there. I'm going to make this sine squared theta minus cosine squared theta. But I didn't want sine squared, I want sine squared minus 1. So if I subtract 1 from both sides, I don't know what that is, sine squared theta minus 1 equals cosine squared theta. So sine squared theta minus 1 is the same thing as cosine squared theta. So I can take this numerator, and when we're writing everybody out, it's really just cosine squared of theta. Yes?
Why isn't the cosine negative?
Exactly should be. Good catch, because 100% it should be negative.
Because it was totally testing you to make sure you're paying attention.
Because we subtracted cosine. So then we're going to take our denominator and write everybody in terms of sine and cosine. So tangent is sine theta over cosine theta times sine of theta minus tangent of theta, which is another sine over cosine. What's up?
When do we need this in real life?
In real life, you'll need it in calculus. 1 and 2. And if you get into any high-level engineering or physics, if you do anything involving circles and real-life measurements and architecture. But as far as like everyday real life, trig is more about problem solving and logic. But I agree, trig is weird. I hate her. She wrote this and I didn't. Okay. So let's figure out this denominator situation. Definitely need to deal with that. Ew, I hate this so much. But still. We're going to simplify this. So we're going to wind up with sine squared over cosine minus sine, oh, don't forget our thetas on either of those. Sine of theta over cosine. All right? Good, we've got cosine squared theta on the top, so. I will change colors because this is getting really blue. I'm gonna change colors real quick because my pen's being a crocus and that blue is getting really smushed together. So I'm gonna erase this. Oop. Alright, this is the line between the two fractions. So those are two separate steps. Two separate steps. I will change colors now in between the different fractions because it's getting very fractiony.
Can you explain, like the part after the minus sign?
Down here?
Yeah.
So this is minus tangent. Minus tangent. Minus tangent. And I just switch it as sine over cosine. So this is still sine over cosine. My handwriting is just awful. All right, so now we have new section. So let's look at this denominator. What's going on here? They already have common denominators, right? So we have now our minus cosine squared theta on the top. And in our denominator, I have sine squared minus sine over cosine.
I'm running out of space and I don't know what to do when I run out of space on this now.
Love that. So when we have fraction inside a fraction, when we have a fraction inside a fraction, what are we going to do? Multiply by the reciprocal. So I'm going to come this way with it, trying not to write on the absolute very bottom. So we have our minus cosine squared of theta times the reciprocal of the bottom. So we have cosine of theta over sine squared theta minus sine theta, which is super gross. And I'm going to go on to another page and write that down again.
Wait, what was the last thing you said?
It says cosine squared of theta times cosine theta over sine squared theta minus sine theta. I'm going to write it again on the next page, bigger and up at the top again, just because I'm out of space, which we love so much. So I'm going to write that again, just so we can simplify a smidge more. We have our minus cosine squared theta times cosine theta over sine squared theta minus the sine of theta. And these are super so gross. And they're super gross. And they will feel super gross forever. Most of the times I tell you it gets better. These don't. They suck forever. They're awful forever and ever. Just saying. Luckily we don't spend too long in the solving of the trig functions because they're gross. But they are what they are. Okay. What can I do next? If it was adding and subtracting, we would need a common denominator. But since it's multiplying, does it have to have a common denominator? No, multiply across. So we have negative cosine squared times cosine gives us cosine cubed of theta over our denominator of sine squared theta minus sine theta. And what we're going to do now is we're going to look at that bottom and say, hey, it looks like there's a common denominator there. Let's see if that helps, or a common factor. Because I could take a sign out of both of those and put it in kind of a factored form situation. Let me change colors again. I know, it looks super gross. I'm sorry, but it's going to look grosser here in just a second. Genuinely, this is not that much better than the last one, but we're going to do it anyway. So we're going to have our minus cosine cubed theta on the top over sine theta times sine theta minus 1. All right, see that common factor? Similar vein, I can take my numerator and make that as cosine times cosine squared and get a cosine and a sine out. So this can be cosine times the opposite of cosine squared.
Where did you get that, the second part?
Up here, I am unmultiplying this together. I'm kind of unmultiplying this step. I took my cosine cubed and make it cosine over sine, because cosine over sine, we can make that a different thing. I can put that as cotangent. I know, it's doing too much. It's a lot. Cotangent theta. And what we have left over on this side is our minus cosine squared. We've done that one before. We did that on the one way that we did up at the top. The secant cotangent one, we did the minus cosine squared there. That was our sine squared minus 1 over sine of theta minus 1. We'd really like to cancel out that denominator. I know. It's going to get briefly worse. I think we have 3 more steps. Because I want us to think of sine squared minus 1, x squared minus 1. If it was x squared minus 1 and I told you to simplify it, what would be your instinct? Let me see. Let me get another color and I'm going to write it for you. The sine squared of theta minus 1, that's something squared minus 1, right? If we had x squared minus 1 in a fraction and we were trying to simplify it, what would we do?
Square root.
Not square root. There's no equal sign here. Factor it. What pattern is it? What would it look like factored if it's x squared minus 1? How would we put this into factored form? It's a difference of squares, right? Well, what if x squared was really sine squared? Yeah, so we can write this. We've got cotangent of theta, and what we really have here is sine of theta plus 1, sine of theta minus 1 over sine of theta minus 1. What happens in the fraction? The sine theta minus 1's cancel out. Get rid of that denominator of grossness. I know, there's a lot. And what we have as our answer, we're there, finally. Cotangent theta sine theta plus 1. That's our answer, because we don't have anything else we can do with our identities. And I know, these are holy cow, what the hex. They are super long, they are way too dang complicated, and they're obnoxious. Okay, but when we see something like this, we're gonna go difference of squares. It's just a funky looking difference of squares. All right. We're gonna oh great. Okay. This is the last one we're gonna look at. I promise it's not quite as gross. Not quite. The last one was the grossest one for today. Definitely. Alright, so it's already in terms of sines and cosines, right? But I see two things that are cubed, and I don't have any cubes in any of my identities to work with. So when we see exponents we don't know what to do, think about it in terms of other things that we might know. So what if this was x cubed plus y cubed? What can we do with that? We worked with something like this last semester. Or x cubed plus 8. Think about when we would factor with our SOAP. This is the sum of cubes, so same, opposite, always positive. Where when we would take our sum of cubes, it would be x plus y, x squared, opposite, x, y, always positive, y squared, like this. We're going to do that same thing with our sine cubed, cosine cubed. X is our sine, y is our cosine. So it's the sum of cubes. So when we come in here to factor this, I'm going to give myself a big old fraction bar. I'm taking my sine and my cosine. So it's going to be sine of x plus cosine of x times sine squared x minus sine x cosine x plus cosine squared x. And I'm going to keep my denominator the same. So it's taking these trig functions and still using our algebraic solving with them. What do we see?
Sine x plus cosine x can cancel out.
I've got a sine x and a plus cosine x on both the top and bottom, so they can cancel out, meaning no more denominator. So we now have sine squared x minus sine x cosine x plus cosine squared x. Well, I know sine squared and cosine squared I have a thing for, so let's put them next to each other. I'm just rearranging, so no signs are going to change. Sine squared x plus cosine squared x minus sine x cosine x. sine squared x plus cosine squared x, that's just this dude. This is my Pythagorean identity. That's the Pythagorean identity. So sine squared x plus cosine squared x, that's 1. 1 minus sine x cosine x. And since it's only in sides and cosines, I don't have any more denominators. I don't have anything I can simplify or change in there. That's your answer. Okay? These are genuinely awful. And yeah. They're confusing and they're weird. Okay? We will continue to work with them tomorrow and practice with them because they're weird. They're so weird. Okay? So knowing these two are pretty intuitive. Knowing these are going to be critical for what we're doing. These Pythagorean identities. We're going to be working with them a lot. We'll practice with this more tomorrow. Okay? Yes, dear.